Hello, students. This is Shudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering. Today, I'm going to give a lecture on electrical circuit and network. The subject is designed for Diploma Electrical Engineering students, second year. So here, it's a single phase AC circuit and resonance. In the unit 2, I already have covered, and this is the last lecture of this session of this unit, unit 2. Without this, there is unit 3, where the principle of circuit analysis is there, AC and DC circuit. It's like mesh analysis, node analysis, voltage and current sources, etc. Now in unit 4, there is the networks theorem statement, procedure, areas of applications and limitations. So source conversion, ideal voltage and current sources, superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, and then numericals is there. So today's topic of discussion is parallel resonance. Okay, so parallel resonance, I already give two lectures on series resonance. One about the concepts of series resonance and the related terms to remember about series resonance. That what is quality factor, what is bandwidth. So, and when the value of XL, that is the inductive reactance equals to the capacitive reactance. So that is actually the resonance. So this part was discussed on that, and then and the second lecture of series resonance was related with the mathematical part, numerical part of the series resonance. Today, I'm going to talk about the parallel resonance. Okay, so here the today's topic of this is the content of today's lecture: parallel resonance introduction, then parallel RLC circuit, resonance frequency, parallel resonance circuit, frequency curve, impedance of a parallel resonance circuit, then current in parallel resonant circuit, then susceptance of a parallel resonance circuit, the bandwidth of parallel resonance circuit, and finally the review part will be there. Now, first, let me talk about what is parallel resonance. The resonance that results when circuit elements are connected with their inductance and capacitance in parallel, so that the impedance of the combination series to maximum at the resonant frequency. Okay, so the resonance that results when circuit elements are connected with their inductance and capacitance in parallel. Okay, so that the impedance of the combinations rises to a maximum at the resonant frequency. So that is about the parallel resonance. Now the introduction. The resonant electrical circuit must have both inductance and capacitance. This is the first and the most important part. Then in addition, resistance will always be present due either to the lack of ideal elements or to the control offered on the shape of the resonance curve. So here the resonance will always be present due either to the lack of ideal elements or to the control offered on the shape of the resonance curve. And then when resonance occurs due to the application of proper frequency, the energy absorbed by one reactive element is the same as that released by another reactive element within the system. So here the resonance frequency, if we talk about the resonance frequency, the frequency at which the inductive and capacitive reactance of parallel resonance circuit is equal. Okay, so look here. The frequency is called the resonant frequency for parallel circuit. The frequency at which the inductive and the capacitive reactances of the parallel resonant circuit are equal. Okay. The frequency at which the parallel impedance of the parallel resonant circuit is maximum. Parallel impedance of a parallel resonant circuit is maximum. It's a frequency. Then the frequency at which the parallel impedance of a parallel resonance circuit has a power factor of unity. Okay, the frequency at which the parallel impedance of a parallel resonance circuit has a power factor unity, the frequency at which. So these are about the resonant frequency. The properties we have to remember about the resonant frequency. Now, this is the calculation of resonant frequency. Look here, in this circuit, one voltage source, AC voltage source is there, and resistance, inductor, and capacitance are connected parallelly. The supply voltage is Vs, the current is Is, the current flowing through the resistance is IR, the current flowing through the inductor is IL, and the current flowing through the capacitor is IC. The simple parallel resonance circuit, tank circuit. Now, since we know that the equations for determining the reactance of each element at a given frequency, and we are looking for that point where the two reactances are equal to each other, we can set the two reactance formula equal to each other and solve the frequency algebraically. Okay, so this is the circuit diagram of the parallel RLC circuit. Now here, look, the XL, we all know that the equation of XL is 2 pi FL and XC is 1 by 2 pi omega FC, that is 1 by 2 pi FC, and this is 2 pi FL. Now resonant occur when XL equals to XC. You already know this from the series parallel series resonance circuit. So when XL equals to XC, we can say 2 pi FL equals to 1 by 2 pi FC. So no problem with this. Then the value of F square will be equals to 1 by 2 pi FL and into 2 pi FC. So that is equals to 1 by 4 pi square LC. So the value of F will be equals to root over 1 by 4 pi square LC. Now here the FR is 1 by 2 pi root over LC, and omega r equals to 1 by root over LC, because you all know that the relation between omega and f equals to omega equals to 2 pi f, right? So just replacing the value in case of fr, if we replace it with omega, then this equation will come, because here f equals to 1 by 2 pi root over LC, and from these relation we can say that f equals to omega by 2 pi. So just put it here, f equals to omega by 2 pi, that is equals to 1 by 2 pi root over LC. So this one will vanish. So finally the value of omega will be equals to 1 by root over LC. So in this way we can prove we can derive the equation of resonant frequency and also the value of omega r, angular frequency. Now here this is a formula to tell us the resonant frequency of a tank circuit given the values of inductance L in Henry and capacitance C in Farad. So this is a formula to tell us the resonant frequency of a tank circuit given the values of inductance L in Henry and capacitance in Farad. So this is the phasor diagram for parallel resonance circuit. The first one is before below FR, then it is above FR, then it is at resonance. So at resonance, So IL and IC, this is rear X phase, VS is along X axis. IC, you all know that the capacitive current always lag 90 degree, positive 90 degree from the supply voltage, and lead 90 degree capacitive current, and inductive current lag 90 degrees. So here if the value of Is equals to IL minus IC, then it will go through IC, and if IL minus IC, no, this should be IC minus IL, and this is IL minus IC, so it will go through the value of Is will go through the IL is the diagram of the parallel circuit. So this part is wrong. We have to identify this. Now this is the parallel resonance circuit. So here the parallel resonance circuit is resistive at the resonant frequency. At resonance XL equals to XC, the reactive components cancel. The impedance is maximum at resonance. Yes. Below the resonant frequency, the parallel resonant circuit looks inductive since the impedance of the inductor is lower, drawing the larger proportion of current. Above resonance, the capacitive reactance decreases, drawing the larger current, thus taking on a capacitive characteristic. Here the frequency curve of parallel resonance, you can find this is the inductive. If it is inductive, then you will find this part, and this is for capacitive. So for inductive, and this is the frequency at resistive point. So this is the frequency curve for parallel resonance. Okay. Now moving to the next slide, the impedance of parallel resonance circuit. Here the figure is showing the impedance peak at resonance. So this is Z in ohms, and this is the frequency along x-axis, along y-axis is the impedance. Now from the given graph, you can see that the impedance is maximum at resonance in parallel resonance circuit, but decreases above or below resonance. Okay, so it is decreases above or below the resonance. Yes, at resonance frequency it is maximum. Voltage is at a peak at resonance since voltage is proportional to the impedance. So you can say that E proportional to Z. Voltage is proportional to the impedance for the parallel resonance. Now current in a parallel resonance circuit. So how the current characteristics look like for parallel resonance circuits. So here you can find at resonance the current flowing through the circuit is at its minimum as the inductive and capacitive branch current are equal. So inductive and capacitive branch current is IL equals to IC and are 180 degree out of phase. So for that reason, the current is the minimum current at the resonant point. This is minimum as the inductive and capacitive is equal and 180 degree out of phase. Now we remember that the total current flowing in a parallel RLC circuit is equal to the vector sum of the individual branch current for a given frequency is calculated as what is actually this? Let me explain. Here the IR equals to V by R. This is the current across the resistor. IL equals to V by XL, current across the inductor, and XL equals to 2 pi FL. So V by 2 pi FL. So IC is same like V by XC. So it is V into, you know, that X equals to 1 by 2 pi FC. So this will be V into 2 pi FC. This is 1 by So here x equals to 1 by 2 pi fc. For that reason, it is v into 2 pi f. Okay. Now, therefore, it, the vector sum of IR plus IL plus IC. So we can say the total current equals to root over IR square plus IL plus IC whole square. So now at resonance, current IL and IC are equal and cancelling. So that we are writing here the IL equals to IC. So IL and IL are equal and cancelling, giving a net reactive current equal to 0. Then the resonance, the above equation becomes IT equals to root over I square plus 0 square, because IL plus IC equals to 0. So the value of I total current will be equals to the current flowing through the resistor. That resonance for parallel RLC circuit. So now I am going to talk about the susceptance at resonance. So the inductive susceptance BL is inversely proportional to the frequency as represented by the hyperbolic curve. The capacitive susceptance BC is directly proportional to the frequency and therefore represented by a straight line. The final curve shows the plot of total susceptance of the parallel resonance curve versus the frequency and is the difference between the two susceptances. Here, look, the inductive susceptance, that is BL, is inversely, okay, it is inversely proportional to the frequency by as represented in the hyperbolic curve. Okay, so from the curve we can conclude this. The capacitive susceptance is represented with BC and that is directly proportional to the frequency, that is, and is therefore represented by a straight line. Okay. And the last one, the final curve shows that the plot of the total susceptance of parallel resonance. The final curve shows the plot of total susceptance of parallel resonance circuit versus the frequency is the difference between the two susceptances. Okay. So this is the susceptance for the resonance circuit. Now at the resonant frequency point where it crosses the horizontal axis, the total circuit susceptance is 0. So this is first one, inductive susceptance. This is capacitive susceptance, and this is the total susceptance. Okay, so vector sum of these two. Now the bandwidth of a parallel resonance, you know, you have the basic idea regarding the bandwidth. This is the difference between the high frequency to the low frequency. High frequency is represented with FH and low frequency FL. So here for this diagram, if you take the value, so bandwidth equals to delta F, that is FH minus FL, 343 minus 281, that is 62. So FL equals to FC minus delta F by 2. So the value of FL equals to 281 and FH equals to FC plus delta F by 2. We can find the value 343 from the diagram. So already know the process that how this is actually the equation. Now the quality factor Q equals to FC by bandwidth. So the FC is 312. The capacity frequency divided by the bandwidth, which is calculated 62. So the value of quality factor will be 5. So the bandwidth of parallel resonant response curve is measured between the half power point. The corresponds to the 70.7% voltage points, since power is proportional to E square into 0.07 whole square, that is 0.5. Since voltage is proportional to the impedance, we may use the impedance curve. Okay, so this is the way to find the bandwidth, the low frequency, high frequency, and quality factor. So at last, I can say that either side of the resonance of the current IL minus IC, and that resonance reactive current is zero. So finally, I can conclude with resonance parallel RLC circuit acts like an open circuit. Current at resonant is at its minimum. Then impedance of parallel resonant circuit is maximum and is equal to the resistance. This resistance is known as dynamic resistance. Susceptance at resonant frequency is equal to zero. So these are the conclusion part of this lecture. If anyone have any doubts, so this is the reference I used. So please let me know for any doubt so that I can clear the doubt my best. Thank you all. Thank you for watching the video. Bye.